Good evening, Professor Younger.
How's it going?
It's going. Been a crazy week, but we're getting through it.
Yeah, it's all we can do. Just take it one day at a time, man.
Yeah, that's what I have to keep telling myself. Otherwise, I don't know. I don't think I'd get through it.
Yeah, especially with all this quarantine crap. That's just a pain in the butt.
Agreed.
I have posted the next test. It's due 1 week from today. And that goes up through chapter 31. So make sure you guys get that done. I posted the practice test last week, so there's been plenty of time to hit the practice test. And I'm still posting more videos. In fact, I neglected to post last week's video on Canvas last week, so I will do that right after class. I don't know why I didn't do it. I must have just forgot. But I have been posting the documents. I noticed they're all up to date, but evidently I didn't post the last video. So I will make sure I post that right after class. It'll be on my YouTube channel. I've also posted a new list of the YouTube videos I have on my YouTube channel. So y'all can check that out.
Thank you.
And we had 3 students and just lost one that logged in, and as soon as I allowed her in, she disappeared. I guess it's something with her internet connection or whatever. Austin or Maria, do you guys have any questions?
Not currently.
Okay. Nothing looked that confusing or worrisome or anything like that?
I think for me personally, I think it just helps for me to kind of go back. But I mean, the way that you explain it is pretty clear. So once I review over everything, I feel like I'm pretty good.
In
For
a
the
good
most
spot.
part.
That's cool. Yeah, I'm noticing not very many people are needing to watch the videos, or at least they're just not watching the videos. So that's fine with me, as long as they're doing well. If you're having problems, though, that would upset me. But it looks like everybody's doing fairly decently as far as grades go. So
I did have one question though. If there was a problem that I was struggling with, would I be able to work it out and then email it to you and see where
yeah,
I
absolutely.
messed up? Okay.
Yeah, do that. Specifically, if you're doing one like on a practice test or homework, take a screenshot of it so I can see not only the full breadth of the question, but also like if it's multiple choice, what the various choices are, especially with multiple choice tests, because sometimes you find that the multiple choice answer that you've chosen is not a bad answer. It's just not the best answer.
Okay.
And that takes a little more nuance. But yeah, if you work one out, just do that. Another thing I recommend you guys do, like I was having some problems with one I sent my 241 class a note about, and I realized the problem that the student was having difficulty with was number 36-24. So I looked in the book, and sure enough, it's the exact same problem from the end of the chapter. So sometimes you can find the problem from the end of the chapter that matches it. And if it's an odd, then you've got the answer already there. So you can try to work it out, get that right answer. And then when you go and do it online, the equivalent version will have slightly different numbers, but you'll already know how to do it. So that's another avenue to follow when you're trying to figure stuff out.
Okay, sweet. I appreciate that.
No problem. Yeah, but anytime you want to, send me any work you can. As neat as you can be with the work that you do will make it easier for me to figure out what you're doing. But other than that, yeah, I don't mind that at all.
Alrighty.
How's it going, Jamie? I see you just logged in, as well as Corey and Sean and Dylan, Elizabeth. Anybody have any questions before we get cracking?
I did, but the answer is written on the thing.
About the test. Oh, see, this is like one of those days where I just happen to be a good instructor. Luck would have it, that is.
Mind reader.
All right. Well, I'll go ahead and get started. We were in chapter 17, and the good news is chapter 17, 18, and 19 are probably stuff you've seen a lot of before, like in chemistry or something like that. So if you had a chemistry course, you probably had some of this, because some of it's the ideal gas law, some of it's kinetic theory, stuff like that. So that might be a little easier. Plus, some of the stuff that's covered other places I won't cover in that much detail. There's a lot of stuff I can do, for instance, with the ideal gas law. But because that's normally covered in chemistry so well, then, why bother? Because you're going to get a better dose of it in chemistry, inorganic chemistry, the intro chemistry, than we get here. So it's not really no need to go much farther. The other stuff, the first law of thermodynamics, which is really just conservation of energy, that you'll do in chemistry as well. You'll do it mostly in different units, but you'll still do it. So we won't have to do too terribly much there. But today I'm going to finish up chapter 17. I'm going to jump into 18, hopefully. So if no one has any other questions, I'll go ahead and get started. And I don't know why I'm letting you look at the paper instead of me, but it's probably a nice respite for your poor eyes that have been focused on this chubby instructor for so long. So let me go ahead and share my screen. So here's the problems I've written out for today. And like I said, when I'm doing this, guys, I go on a roll sometimes, just showing you how to solve these problems and stuff. I feel bad when I go on a roll, but at the same time, I go on a roll because, I'm enjoying it. I think I'm explaining it pretty well. But if you're not understanding something, then by all means, I want you guys to stop me. So keep that in mind. Definitely stop me at any point if you don't understand something. And don't be embarrassed about it or shy about it. Chances are, if you've got a question, somebody else does too. So just keep that in mind. Oh, good. I thought I lost my glasses. All right, so you can see the problems that we're working today. Hopefully they're big enough for it to make sense to you now. So part one, we're really just starting off with some things that I've started putting those in, like number 1, 2, and 3. These are just things that I think you should know off the top of your head. Obviously, I don't mean to work them all out and all those details, but I'm going to a little bit, at least this time, just to get you used to it. So I suggest you all know Boyle's Law, and Boyle's Law is the Scuba Divers Law. So like if you ever take a scuba diving class, this one they'll teach you over and over and over again, and they'll even have quizzes where they'll ask you what law it's called, and it's called Boyle's Law. Charles's Law, you probably know and just didn't remember it was Charles's Law. Gay Lucent Law, the same thing. So first off, number 1, the state Boyle's Law, Charles's Law, and Gay Lucent Law. I'm going to go ahead and show you these just for good measure. And then from that, we'll get a version of the ideal gas law, because in reality, the ideal gas law is more general than you think. So let me stop sharing for a second, go back to the document. So first off, I asked you to state Boyle's Law. And Boyle's Law basically just says that pressure and volume are inversely related. So notice I wrote pressure directly related 1 over volume. That means they're inverse related. This can also be written as pressure times volume equals a constant. That's certainly an acceptable way as well. And it's the scuba diver's law, because the fundamental rule of scuba diving is never hold your breath, never hold your breath, never hold your breath, right? And the reason why they say that is as you ascend, if you hold your breath, the pressure in your lungs will stay the same. But as you ascend, the pressure on the outside will actually get less. So your lung volume will actually expand and you'll pop your lung. And that's called an arterial gas embolism. And it's one of the deadliest things that can happen to you as a scuba diver. So that's why they call it the scuba diver's law. In fact, even if you're swimming up, you should at least leave like a vent of your mouth open so that air can expand. It's kind of weird. I was down about 35 feet and we had to do a ditch exercise where you lose your equipment and stuff like that. And it was weird because I started to exhale like I was supposed to, but I realized I was short on air. So I didn't think I had much air left in me. But upon going up the full 30 feet, I didn't run out of air at all because my lungs were expanding so much just because I was ascending, that I was really surprised by how much bigger the air column in my lungs got. And of course, that's a hallmark of what could kill you. So be careful with that. It only takes about 3 to 6 feet change in depth for you to cause damage, but that's Boyle's Law. Charles' Law, I call the empty bottle or collapsed bottle law, just to keep you in memory of it. So if you've ever left, for instance, a glass of, or excuse me, a water bottle in your car overnight, especially on a summer night or something like that, what'll happen is the water bottle will get kind of warm, and the gas above it, of course, will get kind of warm from being in the car. But then overnight it'll get cold, and what you'll find is the bottle's more or less collapsed. And the reason the bottle collapsed is because volume and temperature are directly related. So you can also write this as V over T equals a constant. So what happened was, since the temperature went down, the volume went down. So when you come out in the morning where it's, maybe 62 degrees or something like that, and it was maybe 80 when you went to bed, then, or maybe 80 when you left the thing in there, then what's happened is the column or the air inside of the bottle has decreased in temperature so much that it caused the volume that it would take up to be smaller, and therefore the bottom is more or less crushed itself. I do this as a demonstration in my physics demos that I do. I'll take a little bit of a gas can, actually an empty gas can, one that's never been used for gas because it's highly dangerous otherwise. And I put just a tad bit of water in it, and I put it over a Bunsen burner so that it gets really hot, and I can get it up to steam temperatures. And I plug it up with a cork and thrust it under a vat or cooler full of ice cold water, and immediately that big metal can, it's a pretty impressive sight, will completely collapse. And the same thing's going there. Specifically, I've decreased the temperature of the air inside by dousing it in water. That's caused the volume to collapse, and it actually is crushed. You can also look at that as the pressure inside crushing, becoming very small, and the atmosphere pressure crushing it. But that's like once removed. You got to think about something and then what something else is happening is doing to it. So the last law is the Gay Lucent Law. And this one, if you've ever had like a balloon and left it by a fireplace or a heater vent, you'll come back and realize the balloon is super blown up, like it's gotten a lot bigger. And that's basically that pressure and temperature are directly related. So again, you can say P over T is equal to a constant. And the reason why that balloon, why that happened to that balloon is basically by elevating the temperature of the balloon by leaving it by the fireplace, you've caused the pressure of the gas inside to increase. And that, of course, has caused the membrane that is the balloon to actually expand. Now, if you put all these together, you can see all these are a constant, and you get V and P on the top, just like this. So ultimately, you get P, V over T equals a constant. And in some sense, this is the generalized ideal gas law. It just says that pressure and volume are inversely related, pressure and temperature are directly related, and volume and temperature are directly related, as long as you don't change the number of moles. So if you actually wanted to make it the ideal gas law, then you're not going to change the number of moles, lowercase m, because in reality, that could actually make all this go up. In fact, if the number of moles went up, then either the pressure goes up or the volume goes up, or possibly both go up, or the temperature goes down. Okay. So that's the ideal gas laws. And these are how they were determined experimentally. Once you put all this together and combine it with the fact that the number of moles is directly related to the pressure or is directly related to the volume, then you ultimately get the new version, which is the ideal gas law, which brings us to question number 2. So if you notice question number 2, it says state the ideal gas law, define each symbol, and give 3 values of the universal gas constant. Again, these are things that you should all know already just from either high school chemistry or college chemistry or whatever. But if you haven't had high school chemistry, don't feel bad. It's not that complicated. We're going to do a very shortened, abbreviated version of it. So let's go ahead and do this now. In this case, you combine all these and combine it with the fact that you could also say P V over NT is equal to a constant. That would actually square up and make all the variables that are relevant. Well, when you do that, you find that P times V is equal to N times R times T. So the real constant here, at least in that case, the real constant is R. In this case, the constant was N times R. P is equal to pressure. Whoa. That's off the P. P is equal to pressure. V is equal to volume. There I go again, right? Leaving off the letters. V is equal to volume. N is equal to the number of moles of the gas you're dealing with. T is equal to temperature, and that's got to be in Kelvin. Okay, that's the key thing. It's got to be in Kelvin. And then R is the universal gas constant. Okay, that might sound like a weird overstating word, but if you're in engineering, you'll see why later. In many engineering thermo classes, that's constant. In many engineering thermo classes, they have a different value of R for every gas that you deal with. So instead of going and taking up the time to look up the molecular mass of a gas, which you'll have to do ultimately if you want to convert this moles to mass in kilograms, what they do is they combine the molecular weight and R, and you get a gas constant for each gas. So they have a slightly different version of the ideal gas law than we do. And that's just, I'm just letting you know that in case you run into it and it looks a little confusing to you. It's no different than this one. Like I said, all they did is sort of combine the R and the molecular weight, because remember, if you take the mass of a substance and divide it by its molecular weight, you'll get the number of moles. So that's where it comes in. Now this has values of 8.314 is the one we normally use in physics, and that's joules per mole Kelvin. There's also one, in case you want to use it in liters, atmospheres of pressure, and moles of Kelvin, and that's 0.0821. That's liters, atmospheres, moles, and Kelvin. And there's another version, 1.99, in case you're in a chemistry class where they like to use a lot of calories, and maybe even some engineering classes, and that's calories per mole Kelvin. Okay, but I generally use this one. Okay, if you have a pressure in atmospheres and volume in liters, or you want volume in liters, and by all means use that one. That'll save you some steps. But that's really the ideal gas law. Anybody in here not familiar or haven't used the ideal gas law before? All right, looks like everybody's used it before. That's a good sign. All right, so let me go back to question number 3 now. So question number 3 is, what is the average atmospheric pressure in pascals, torr, atmosphere, and millimeters of mercury? So this is something that we're going to use over and over with the ideal gas law. So I figured I better introduce it. It turns out the atmospheric pressure is 1.01325 times 10 to the 5th Pascal. Now, Pascal is equal to 1 Newton per square meter. So basically, a pressure of 1 Pascal is about a quarter pounder laying on a 39-inch by 39-inch square. So it's really not that huge amount of pressure. We're asked for it in pascals, which I just listed, torr, ATM, and millimeters of mercury. So I'm going to stop sharing so you can see what I wrote. We usually only use 3 sig figs, so 1.01 times 10 to the 5th pascals is usually enough. But you can also write it as 1.01325 times 10 to the 5th. As I said, a Newton is about a quarter of a pound. It's actually a little less than a quarter of a pound. Actually, yeah, I think it's a little, no, it's a little more than no, it's a little less than a quarter pound. So you basically a quarter pound divided by a square meter, and that's literally about 39 inches by 39 inches. So if you imagine putting a quarter pound hamburger on every 39 inch by 39 inch square, that's how much pressure, atmospheric pressure, or excuse me, 1 Pascal is. That's why the Pascal is such a small unit. That's why this pressure has to be such a big quantity, literally 100,000. Well, the other units are 1 atmosphere, and that's what 1 atmosphere is. So atmospheric pressure in the unit of atmosphere, just like that, is just 1, okay? So if you got 1.01 times 10 to the 5th Pascal, or 1.01325 times 10 to the 5th Pascal, you know that's 1 atmosphere pressure. You also know that that is 760 torr. If I remember correctly, that's named after a scientist by the name of Torricelli, Torricelli. But it's also relevant that it happens to be millimeters of mercury 760 of those as well. Okay. Sorry, I wrote that like that. But basically, the torr is the same thing as millimeters of mercury. So that's another unit of pressure. And what they mean by that is if you took a tube, a glass tube that had one end sealed, like a really long test tube, for instance, it's got to be 760 millimeters as a bare minimum, but you're probably going to need about 800 or 900 millimeters. But anyways, if you took that tube and completely submerged it under mercury and then kept the open end down as you lifted the tube up, what would happen is basically mercury would stay in that tube, and basically all what happened would be there's a little vacuum up above it. That is actually the atmospheric pressure pushing down on the mercury, forcing it to go into almost zero pressure, which is what the vacuum in the top is. Now, if you measure from the top of that pool of mercury up to the top of that level of mercury in the tube, that should be around 760 millimeters or about 76 centimeters. So that's really what that is. Those are good units. Those come in handy. As you can tell, there are no millimeters of mercury or torr values for R, so we're not going to use those with the ideal gas law. Any questions on any of that? So looks like I don't have any questions. At least no one's doing the little question hand symbol. So a common value that every student of physics and chemistry and possibly biology should know is that the volume of 1 mole of gas at standard temperature and pressure. So this is my way of implementing some knowledge on you that you're expected to know, but also, of course, teaching it to you at the same time. So you might not recall or have ever heard of standard temperature and pressure, STP, but it's important. It comes up a lot in physics and chemistry. It's not what you think it is. It's not, 20 degrees Celsius. It is, in fact, 1.01 times 10 to the 5th Pascal or 1 atmosphere of pressure, but the temperature is the weird part. It's actually at the freezing point of water. So 273.15 Kelvin. So STP means T equals 273.15 Kelvin, which equals freezing point of water. And the pressure P is equal to 1 atmosphere, which equals 1.01325 times 10 to the 5th Pascal. Okay, that's what standard temperature pressure is. And what I'm asking you is what is the volume of a gas, 1 mole of gas at that temperature and pressure? So N is equal to 1.00 moles. So we see PV is equal to nRT. Does anybody know why I'm writing the lowercase p in this drawing right here? Anybody know why I do a lowercase p?
Not getting confused with Pascal.
That helps in that case. There's actually a more esoteric reason, and it's actually very helpful when you do know it. So I don't like it being an esoteric reason. The esoteric reason is it's not a extensive variable. So basically, V is a variable that's proportional to mass. So you should keep that uppercase, because when you do the specific value of the volume, that's really the volume divided by the mass, which is 1 over the density. Pressure is not something that changes by multiplying the mass by 2 or something. So they keep that lowercase, and the uppercase ones are normally meant to be the other type of variable. Of course, all bets are off when they do that with temperature, but you'll notice that your book uses a capital P. So I just wanted you to know why I keep writing that way. In this case, we're actually asked for the volume. So I can see volume is equal to nRT over P. The number of moles is 1.00 moles. I'm writing all the units so you'll see what's going on here. I'm going to say 8.314 joules. A joule, remember, is a Newton times a meter. That's joules per mole Kelvin. So you can see that mole is going to cancel out with this mole. And then I'm going to say 273. I'm just going to call it 273 because that's enough. I'm really just looking for 3 sig figs. And then I'll divide that by 1.01 times 10 to the 5th Pascal. When I do all this math, what you end up getting, notice this is a Newton meter. This is a Newton per meter squared. So the top becomes meters squared and the bottom becomes newtons. So the newton in the bottom cancels out with the newton in the top, and the meter squared multiplies by the meter to give me meters cubed. So you can see the volume comes out in cubic meters. So in this case, volume is going to equal 1 times 8.314 times 273 divided by, I'll use a parenthesis. Oh, I didn't even need to use a parenthesis there because it's only one number. But anyways, 1.01 e to the fifth. And in this case, I get 22.40 times 10 to the negative third cubic meters. Now, that means it's basically a milli of a cubic liter of a cubic meter, but obviously that would be really complicated, a millimeter cubed. So we actually have a unit that represents a thousandth of a cubic meter, and that's called a liter. So at 22.40 liters is really enough. I did, by the way, carry out the 1.01325 when I typed that. If you actually put in the 273.15 and then you don't do the 325 on the bottom, you sometimes get something that rounds more closely to 22.5. So I just wanted to make sure y'all got the right quantity here. So really the value that everybody should know off the top of your head is 1 mole of gas, no matter what the gas is, should take up a volume of 22.4 liters. So, and remember a liter is 10 centimeters by 10 centimeters by 10 centimeters. When you see that, then you realize, oh, if I made it 10 times wider, that'd be 100 centimeters. 10 times taller, that'd be another 100 centimeters. And 10 times deeper, that'd be another 100 centimeters. So it'd be 100 centimeters times 100 centimeters times 100 centimeters would be, in fact, 1,000 liters, because each 10 centimeters is a liter. So 1,000 liters you see is a cubic meter, just like we expect. Any questions on that? So this is a quantity that they sort of just at random times instructors expect you to know. So don't be surprised if you're reading along in a textbook and they just randomly say, oh, that's clearly 22.4 liters. You'll be like, well, where did you get that? Okay, so that's where that came from. And that's literally how it happened to me, as well as a couple other of these values that I'll bring up in this problem set. So does anybody have any questions on 1 through 4 yet? All right, so this stuff was mostly pretty straightforward and easy. It's more about facts you should memorize and a quick, easy application of ideal gas law, the ideal gas law. So now I'm going to move to number 5. And it says, given that the pressure at a depth D below the surface of a liquid of density rho is given by P equals the pressure of the atmosphere plus rho times G times D, where P, atmosphere, is the atmospheric pressure above the liquid and G is gravitational acceleration. What is the pressure at 33 feet below the surface of the ocean? Now that's kind of weird because you're probably used to the density of water being 1,000 kilograms per cubic meter. And though I've mentioned this to you a couple times, I'm bringing it up again so you'll know. In salt water, we can basically assume that the pressure or the density of salt water is about 1,025 kilograms per cubic meter. So that's what we're going to use here. I did say 33 feet below, so we're going to have to convert that 33 feet to meters. That turns out to be about 10.058 meters. So we'll get through that. But part A says, if a balloon is filled to a volume of 1 liter, temperature of 30 degrees Celsius and pressure of 1 atmosphere at the surface, how many moles of air will it hold? Notice I said air, I didn't say a specific element. So that makes it a little interesting. B, assuming that the air is 78.1% nitrogen and 20.9% oxygen and about 0.9% argon, all by volume, how many moles will there be in each balloon? Of each in the balloon, I should say. I said of each balloon though. C, how much of the volume and pressure are attributable to the oxygen? And finally, D, what will its volume be at 33 feet below the surface? Okay, so that's a It's a big question. It's got a lot of different parts to it. And the first part, A, is really how many moles of gas there are. Okay, so let me kill this real quick. And what we're using is the ideal gas law. And the ideal gas law says N is equal to, of course, PV over, over RT. That should give me the actual number of moles. So in this case, I'm talking about at the surface. So the pressure is 1.01 times 10 to the 5th Pascal. Again, you don't necessarily have to use units now, but if y'all do this when you're doing your homework, it'll save you a lot of oopsies. They said the volume is going to be 1 liter, and technically 1 liter is 1/1000th of a cubic meter. So you really got to work that out basically. And let me see. I did say 1 liter, didn't I? Let me check my thing again, because I think at one point I decided to make it 2 liters. Nope, it's still 1 liter. So I will keep the 1 liter. And 1 liter is 1.00 times 10 to the negative 3rd cubic meters. And notice the reason I have to do that is the Pascal is Newton per square meter, times a meter cubed gives me a Newton meter, which is a joule, which remember is the unit that we need in the ideal gas constant, the universal gas constant, joules per mole Kelvin. So that's why I had to make sure it's in cubic meters. I divide that by 8.314 joules per mole Kelvin. And then I take that temperature. Did I say that temperature was going to be 30 degrees Celsius, I think? Yeah, 30 degrees Celsius. And that's because I want it to be like a warm summer day, basically. So that's 30 degrees Celsius, which is 303 Kelvin. So when I do all this math, I have to deviate because I had changed when I actually did this work as prepping for class. I ended up using 2 liters. So 1.01 times 10 to the 5th times 1 exponent negative 3 divided by parentheses 8.314 times 307. And I get 0.03957, carrying 1 extra digit, of course, moles. Okay, I use 3 sig figs on everything, so it's 0.0396 should really be what it is, but I'm carrying 1 extra digit as we're supposed to be. Now, part B wants me to answer the question of how many of these moles should be actual oxygen and how much should be nitrogen. Well, it turns out when you give the pressure or the, the percent by volume, you are actually given the percent by mole as well. So 0.781 is the percentage of nitrogen. So if I multiply 0.781 times 0.03957 moles, then what I'll get is...
Professor?
Yes, sir.
For the temperature on part A, I got 303 Kelvin.
Oh, thank you. That was right. I don't know. Oh, yeah, that's right. I was thinking 273. And let me see. Yep, I did write that. So that'd be a definitely different value. Let me make that correction on the fly. So 1.01, whoa. 1.01 e to the 5th times 1 e to the negative 3 divided by parentheses 8.314 times 303, which is absolutely correct. I can't believe I did that. That's 40.09 times 10 to the negative 3rd, so 0.04009 moles instead of the 3957 I said. Okay. So now I'm going to take that number and multiply it by 0.781. And that gives me 31.314 1 times 10 to the negative third moles of N2. Now, this is really going in the weeds a little bit, but I realized this was something that I didn't necessarily get when I took this in physics, so I wanted to make sure you guys are clear of what's going on. When you have a certain pressure and it's made up of a bunch of different gases in there, each gas has a partial pressure, and that partial pressure is basically equal to the total pressure times the molar percentage that it has. So if the gas is 78.1% nitrogen by moles, meaning 78.1 of every 100 moles of the gas is nitrogen, then 0.781% of the pressure will be due to nitrogen, and so on and so forth. So that's why I'm actually taking the time to do this extra stuff. The other part was oxygen, and oxygen turned out to be 0.209 is the basically is the percentage of air that's oxygen. Again, that's volumic, meaning comparing volume that's oxygen to volume that's air. And it's also the same thing as moles of oxygen, O2 to moles of air. So 0.209 times 0.04009 moles. This gives you and hopefully I actually did that correctly. Oh yeah, I did. Okay. And I get 0.00854 0.00848 moles of O2. Again, carrying one extra digit there, just like I did before. So that's the actual moles of oxygen and moles of nitrogen. Remember, air is about 80%, pretty close to 80% nitrogen and 20% oxygen. The other 1% that we have here, 94% of that 1% is essentially argon. You then come up with CO2, which is 4 10,000ths of the mass. Methane is further down at like 6 parts per million, stuff like that. So the rest of it's in there. It's just really the main three is nitrogen, nitrogen, oxygen, and argon. So there's our part B. Let's see what other crazy question Mr. Younger asked. Assuming that 78 and gotcha, how many moles will there be of each in the balloon? So you can see basically 0.08548 moles of oxygen in the balloon and 0.03131 moles of nitrogen. Now, how much of the volume and pressure are attributable to the oxygen? So this is the Dalton's law of partial pressures is what we're getting at. And again, this is the part that I didn't understand that well when I had my physics class. So I wanted to make sure you guys reiterate it. What it basically says is that the total pressure, the one that comes out of the ideal gas law, that P, okay, that total pressure is equal to, hold on a second, better stop sharing. That total pressure is equal to X1 times P1, where X1 is the mole fraction for gas P1. Okay, so whatever gas you call one, in this case, we'd say it's nitrogen, then the molar fraction of the gas that's nitrogen, if you take the number of moles that's nitrogen divided by the total number of moles present, you get this quantity, and then you multiply that by P1, which would be the partial pressure due to nitrogen. Then you do the same thing plus X2, P2 plus ... That's really Dalton's law of partial pressures. And it just says that the sum of the fractional or partial pressures is equal to the total pressure. So whenever you multiply these percentages that we're getting, this 0.781, this point, again, assuming it's molar percentages, which is what volume percentages work out to be, then all you have to do is multiply this times the total pressure, and you'll actually get, well, you can see P1 would actually be P total minus all the other things divided by X1. But that's basically how you're getting it. So that's what Dalton's law is. And it just says, hey, you know, over top of water, you're going to have some vapor pressure. That's due to water. You're really supposed to add that in first when you're using P on PV equals nRT. So that's really why I'm showing you all that. So in this part, they're saying what fraction of this is due to the actual gas nitrogen. So this X1 P1 is actually due to the pressure of nitrogen. And what we're going to say is X1 P1 plus X2 P2 plus, I'm going to say X3 P3 for argon is equal to P total, which we found the total pressure to be, of course, it was 1 atmosphere. So that's 1.01 times 10 to the 5th Pascal. Now, this percentage right here is 0.781. This percentage right here is 0.209. And this one, you can basically say is the rest. And I think you essentially have to call that 0.010. Okay. So what you need is really subtracting this part and this part from the P total. I would say P total minus X2 P2 minus X3 P3 is actually equal to X1 P1. So that means P1 should actually be equal to 1.01 times 10 to the 5th Pascal minus 0.209 times the P2 plus 0.01 times the P3. And all that divided by 0.781 should be the pressure. I think you can see, though, that this number is going to be so small, you might as well just assume that's that, and you get a pretty good estimate. And that's really what we're going to do. So we can say P1 is really, really close to 1.01 times 10 to the 5th Pascal divided by 0.781. Whoa, no, that can't be right. Okay, do y'all see why this can't be right? Anybody know what's going on there? If I divide 1.01 times 10 to the 5th, which is, you know, 101,000 by 0.781, I'm going to get a number way bigger than atmospheric pressure, aren't I? So I was actually doing this little last part on the fly. I shouldn't have done that because obviously I made a mistake. Now this part right here is all correct, so that's good. What I'm going to tell you to do is that really the pressure P1, so let's cancel out this part and cancel out this junk. I'm just going to say P1 is approximately equal to 0.781 times 1.01 times 10 to the 5th Pascal. Okay, that's really what I was shooting for, which would have resulted in that. But when I realized I was dividing by 0.781, I knew I screwed something up. So I will reinvestigate that a little later. But 1.01 10 to the 5th times 0.781 gives me about 78.88. Now I know why when I did it with 2 liters, it worked out okay, because I kept getting a number that was smaller than the 1.01 times 10 to the 5th Pascal, because I was literally doing 2 atmospheres. So anyways, pressure due to N2 should be about 78 or 7.8 times 10 to the 4th. Let me see, 7.8 times 10 to the 4th Pascal. And the pressure of O2 should be, again, about 0.209 times 1.01 times 10 to the 5th Pascal. And in this case, I get 2.11 times 10 to the 4th Pascal. So sadly, I wanted to make sure y'all didn't miss that Dalton's law of partial pressures, and I made a careless mistake in explaining it, so I kind of ruined that. But anyways, the big deal is, yes, this is how it's done. You're not allowed to just blindly say the pressure is P and just run with it. You actually have to take into account, for instance, if you're doing the pressure of a gas over top of a liquid in a test tube, then you have to figure out the vapor pressure of that test tube, or excuse me, of that substance that you got into the test tube. And then part of that pressure has to be coming from that, and the rest will come from the other gas. So when you go to use the ideal gas law to figure out what gas is present and how many moles, if you don't correct for that, it'll be an error. So that's the main reason for me to show you that, just because, like I said, I made numerous mistakes, which I made again today. But anyways, hopefully that'll help a little bit. I think that was the last part of number 5. Let me double check. Oh no, number 5, there was one more part, and this is the main part that's more of a physics problem as opposed to a chemistry problem. And what they're asking is, what happens if I take this 1 liter balloon? So the balloon has a volume of 1 liter. It's been tied off, and it's sitting at the surface of the ocean, and I pull it underwater to 33 feet. Well, it turns out at 33 feet, P is equal to P atmosphere, which is 1.01 times 10 to the 5th Pascal, plus the density of seawater, which is 1,025 kilograms per cubic meter, times 9.80 meters per second every second, times 10.058 meters. That's how deep 33 feet is. And what you end up getting is 2.02 times 10 to the 5th Pascal, which is 2 atmospheres. Okay. So that is the atmosphere. That's the pressure inside the balloon now. That's actually the pressure of the air as well, or excuse me, the water as well. When you bring it down from sea level, where the pressure is 1 atmosphere, down to 33 feet, the pressure will be 2 atmospheres. And then because of the ideal gas law, which may be written, as I was hinting at before, as PV over T equals a constant. Since the container was closed, the end's not going to change, so I don't need that version. I just need this version. And in this case, if we assume it's done quick enough, then the temperature is not going to change. And all we'll get is that P2 is equal to, or excuse me, V2, the volume when it's at depth, is equal to P1 over P2 times V1. Well, V1 was 1 liter. The pressure at the top was 1 atmosphere. The pressure at the bottom was 2 atmospheres. So you can see it's going to be 0.500 liters. And that is the answer for part D. So I really should block that off in a little bit different color. Notice how when I use this version, when I use PV over T equals a constant, like this right here, I still have to use Kelvin for temperature, but I can use anything I want to for pressure and volume, long as I use the same thing in every place where I put that pressure. So here I just use atmospheres. Why waste time doing 1.01 times 10 to the 5th? I can just do 1 atmosphere over 2 atmospheres times 1 liter gives me 0.5 liters. Okay. And yes, this is exactly consistent. If you have taken a scuba diving class, they will tell you that your pressure at 33 feet is twice the pressure at 1 foot. And that's why the first 33 feet of your scuba diving depth are the most dangerous, because that's the largest change in pressure over any one step. So we're going a step of 33 feet. You're going to change from a pressure, if I'm at 33 feet down to 0 feet, you're going to change from 2 atmospheres of pressure, or roughly 29.4 PSI, down to 14.7 PSI. Whereas you go from, let's say, 66 feet to 33 feet, you're only going to go from 3 atmospheres to 2 atmospheres. That's only, basically 2/3 change, whereas the other one's a whole 100% change. And if you go from 99 feet to 66 feet, you're going to go from 4 atmospheres to 3 atmospheres, and so on and so forth. So really, the most pressing and potentially dangerous as the last 33 feet of scuba diving. That's also why we normally have a staged platform at 15 feet where you can do your decompression just for safety. So when you're coming up from a dive to say 100 feet or whatever, it's always good to take a break at the 15 foot mark and just rest there for several minutes, just in case you've got any extra nitrogen buildup in your blood due to ascending a little too fast. Okay. Again, that's way in the bushes as far as the physics class goes. That's way in the bushes for scuba, but it's still pretty important, interesting stuff to know. Any questions on that one? Okay, so there's some other neat stuff that I want you to be able to do and know in general. Some of these are just surprising facts. So let me share the screen again. We just did 5. It says, write the ideal gas law in terms of the number of molecules instead of the number of moles. Now, this is a pretty important thing, as we'll see in kinetic theory, which is chapter 18, because we're going to make use of the ideal gas law in that version. So here it is. What we have for number 6 is the ideal gas law, and we're wanting to write it as the ideal gas law where n is in it as opposed to lowercase n. So right now we have PV equals nRT, where n is the number of moles. What we want is to write this in terms of big N, the number of molecules. So big N equals number of molecules or atoms. And of course, that's actually equal to the number of moles times Avogadro's number. That's really how you get that. So you can see from this that little n is in fact equal to n over Na. So I can now write PV equals n over Na, where Na is Avogadro's number times RT. Now, the neat thing is R, the universal gas constant, divided by Na is another constant altogether, and it's called the Boltzmann constant, K sub B. It's equal to 1.3807 times 10 to the negative 23rd joules per Kelvin. So now I can write PV is equal to N, the number of molecules or atoms, times KB times T. Oh, excuse me, I left off my V. Okay. So that is the ideal gas law in terms of the number of molecules or atoms instead of in terms of the number of moles. And it's what we call an equation of state. So for a gas, there are variables: pressure, volume, temperature, number of moles. These are all variables that can affect one another. And in fact, whenever you have an equation that relates all of them, that equation is called an equation of state. So this is an equation of state, and it's very important. It's one of the most important physical laws we can ever come up with, is an equation of state. And there's equation of states, for instance, for gas. There's an equation of state for a rubber band, which oddly enough doesn't, need pressure and volume and all that stuff. It just needs basically its length versus its stretched length. But yeah, there's a lot of equations of state. So I just want to let you know that's an equation of state. We've now derived it in terms of the big N instead of the lowercase n. And again, when I go to chapter 18, that'll make more sense. And it'll come in handy. So now let's go to number 7. No one has any questions on that, right? Or does anyone have any questions? Let me not assume. Okay, so here's a neat problem that I usually make my conceptual physics students do. And it's sort of the Fermi problems that your book talks about, the Fermi, F-E-R-M-I, should be pronounced Fermi instead of Fermi. But basically, you should be able to estimate certain things. And one of the things you might be surprised about is when you estimate the amount of air in a room in terms of kilograms, how much mass of air is there in a given room, you'll be surprised at how big it is. So for instance, a typical classroom like at TCC, or even bigger ones that you might see at a university. I've had some classrooms that hold 600 or 700 students. But a typical classroom might be 30 meters by 40 meters by 3 meters. So, 3 meters is about the height. So it's, around a 9 or 10 foot ceiling. The 30 meters is, of course, around 60 feet. The 40 meters is around 130 feet, something like that. So what I'm asking you here is, what is that volume in meters? B, what is that volume in liters? Again, we know that 1 liter is 1/1000th of a cubic meter, so that'll help you. And then I say, before applying the ideal gas law, estimate the mass of the air in the room by realizing that the density of air is about 1/1000th the density of water. In fact, the density of water is 1,000 kilograms per cubic meter, and the density of air is 1.29. So if you actually use the 1.29 as opposed to just 1, you'll get a much more accurate figure. But even just using 1 gets you a pretty good estimate. So let's start off by doing that problem. Anybody have any questions about it before we go on? So we're going to say the volume is equal to 30 meters by 40 meters by 3 meters. 3 times 4 is 12 times 3 is 36. And then a 0 and a 0, so that's 3,600 cubic meters. That's the actual volume in cubic meters. And that's exactly right. Nothing we need to do about that. In part B, we want to know what that volume is in liters. Well, 1 cubic meter is 1,000 liters. So this actually has to be multiplied by 1,000. So I'd say the volume is 3.60 times 10 to the 6th liters. Okay, that's really what the volume is in liters. It's literally 1,000 times larger. Now in part C, I ask you to estimate that. So we know the density of water is 1,000 kilograms per cubic meter. And if we say the mass is approximately 3,600 cubic meters times 1/1000th of 1,000 kilograms per cubic meter, I think you can see what happens. The cubic meters obviously is going to cancel out with the cubic meter, and the 1,000 is going to cancel out with the 1,000. So I'll end up getting 3,600 kilograms. Now remember, 1,000 kilograms is about 2,200 pounds. Okay, that's what's called a ton. It's also called a metric ton. Now, a metric ton and a ton is also called well, they refer to that as the bigger of the 2 tons. There's also a short ton, and a short ton's 2,000 pounds as opposed to 2,200. So 2,000 pounds is a short ton. All right, it's also considered a British ton. So when we're talking about a half-ton truck, we mean that that half-ton truck supposedly can tow 1,000 pounds. In actuality, almost all half-ton trucks can tow well over 1,000 pounds safely without damaging the engines, but that's where the name came from. So just keep in mind, this is a metric ton, which is 2,200 pounds more likely, and that's actually a tall ton, if you will, and that's 1,000 kilograms. So what we're looking at here is basically 3.6 metric tons on estimate. Now, if I actually use the better figure, then I'd say M is more like 3,600 cubic meters times the density of air is 1.29 kilograms per cubic meter. When you do that math, lo and behold, you get a quite significant difference. You get 4,644 kilograms. Okay, so now we're talking on the order of 4.6 tons with 2 N's and an E. Okay, so that's pretty huge. You know, a room like the size of a typical classroom, 60 by 130 roughly. Yeah, that's several tons of air. That's pretty impressive, right? All right, now that we've done that, I can ask for part D, which is use the ideal gas law to actually compute it. Well, N is equal, well, if I want the mass of the room, of the air, then I need to take the number of moles of air and multiply it by the molecular weight of air, which I actually have looked up, by the way. It's kind of nice to have. And that's literally just by taking the 0.781 and multiplying it by the molecular weight of nitrogen, which is about 28.02 because it's N2, not N1, and taking the 0.209, multiplying that by the molecular weight of oxygen, which is about 16.001. Actually 16.004 or something like that. And then doing it again for argon. But basically with that, we can get it. So I know that the number of moles of air is just given by the ideal gas law. So I'll say PV over RT and then times the molecular weight of air. So I'm going to say the mass of the air in the classroom should be roughly equal to 1.01 times 10 to the 5th Pascal for the pressure. The volume we found was 3,600 cubic meters. The R is 8.314 joules per mole Kelvin. And then here's the temperature, which I'll remind you up here. I tried to use a fairly accurate figure. So a typical classroom, for instance, air in the room weighs, excuse me, I need to put an S on that. At 20 Kelvin, well, 20 Kelvin, 20 degrees Celsius, that's obviously a bit of a problem. 20 Kelvin would be a non-realistic room. And I'll do this, I'll do insert special. Sorry, this is taking time that y'all shouldn't be subjected to, but here we are. So that's 293 Kelvin. So 293 Kelvin should be close enough. And then I'm going to multiply that by the the molecular weight of air, which is about 28.96 grams per mole. And of course, that's going to come out in grams instead of kilograms. So then I got to take 1,000 grams and divide that into 1 kilogram and multiply all that by that. And when I do that, I will ultimately get 4,323 kilograms. Notice that's pretty darn close. And the reason why it's not exactly the same is I arbitrarily chose 20 degrees Celsius. The density of air obviously changes for various temperatures and stuff like that. So, you know, it's amazing that we got that close. Let's put it that way. So 28.96 grams per mole was the actual molecular weight. And from all that math, I got 4,323 kilograms. So again, this is about 4.3 tons or 4.3 metric tons for the air in that classroom. Anybody surprised that the air in a classroom would weigh that much?
Yes.
Yeah, the good news is if you're like an upstairs floor, you don't have to worry about it too much because the air pressure below it is just enough to cover exactly that. So you don't have to actually take into account the air weight when you're dealing with designing buildings and stuff like that, because the pressure inside is equal to pressure outside until you get a tornado or a hurricane. And that's why it's sort of important that your windows not bust, or that if your windows did bust, exactly the right number of windows busted is very important, because you could have a ton more pressure on one side than the other side if too much was getting out or if too little was getting out. So those are always problems to deal with in terms of structural engineering aspects. So that's it. That finishes chapter 17. I've given you sort of all the types of examples you can expect. You'll see there's more of them. Of course, there's lots of other types of things I can do with the ideal gas law to ask you, but this covers the majority of what we do, especially for chapter 17. So if no one has any questions, we'll jump on into chapter 18. Anyone have anything? Okay, so I'm going to do something really cool here. I'm going to derive the ideal gas law. So we're going to use the kinetic theory of gases, which is basically just the idea that all solids, all objects are made up, all substances are made up of atoms or molecules. And we're going to treat those atoms or molecules as if they're the smallest thing there is. So no energy can be lost in their collisions. If they were, you know, it'd have to be stuff where something small got broken into something smaller or something weird like that. If you made sound, that would have to be comparable to the wavelengths would have to be comparable to the size of the atoms and molecules. And that's not the way sound works for us. So a lot of that is automatically fulfilled by atoms and molecules. And we're just going to assume that they're moving, and they're moving in direct relationship to their temperature. The idea is that, in fact, ultimately, if you take the kinetic energy of an object moving in and out or left, right, or up and down in the three translational directions, if you take the kinetic energy due to those motions and find the average of it for each of the molecules and atoms in the substance, and then you sort of multiply that by some arbitrary number, if you will, then that'll give you a temperature scale. And in other words, the higher the temperature, the higher the kinetic energy of the atoms and molecules. So we're going to use that idea to come up with an equation of state, something that relates macroscopic variables like pressure, volume, to microscopic variables, which until now was really a macroscopic variable, temperature was, but now we can see, oh, there's a relationship between the microscopic and the macroscopic, specifically the average kinetic energy of the microscopic atoms and molecules is related to it. So let me start with that. So I've done the problems. I'm going to pull this sheet away and start with a new sheet of paper. And what I'm going to do is I'm going to imagine a box in space. It'll be a perfect cube, if you will. And I'll say the cube has a length, width, and height all equal to L. So this is L, this is L. And in fact, this is L as well. Okay, and now we'll imagine this could be x-axis, this could be the y. I know y'all not seeing this stuff right yet, hold on. I will imagine that this is the x-axis, this is the y-axis, and this is the z-axis. Notice by doing that, it makes a right-handed coordinate system, yada, yada, yada. So in general, any particular molecule or atom could be moving in any particular direction at any particular time. And we're going to try to capture that essence, if you will, by analyzing this. So what I'm going to say is I have to realize that if I'm wanting to calculate the pressure on, say, a particular side, let's say this side, that pressure, P, is equal to the force divided by the area. Of course, the area is just L squared, but the force really is related to the change in momentum of a particle as a particle, for instance, comes up, hits the wall, and then bounces off, right? So this is related to, I don't know what I wrote there, but evidently some letters came out that were sort of right, related to change in momentum of atoms, molecules, ... Okay, so what I can say is whenever an object like an atom or whatever of mass m strikes a wall, then you might look at it as a change in momentum, delta P, which equals change in mass times velocity. That's actually equal to mass times velocity final minus mass times velocity initial. Now, if you assume the collision is elastic, then the velocity initial and the velocity final will actually be equal to each other. So if we look right here and we say, let's take for a second, forget about the issue of it actually moving at a direction that's perpendicular to the wall as well as a direction that's parallel to the wall, because that is a real thing. That's actually happening, right? This is V, and this is, let's say, V sub Y, according to that drawing. And this, of course, is V sub Z, according to this drawing as well, right? So forget about the fact that we're just dealing with this particular value, because we'll deal with that later, the fact that we're just doing, say, the Y-axis. But what we know is after the collision, this thing's going to come in like this, hit here, and then it's going to come back off. And because it's an elastic collision, then the momentum before equals the momentum after is always true, but the kinetic energy being before equaling the kinetic energy after means that the Vy final is equal to Vy initial. Okay, and the same thing with the Vz, which happens to be right here. The only difference is, of course, is a negative absolute value, but in the Vz case, it's actually just the same. So what we can do is we can now say this will be delta P sub Y, which we could change for X or for Z, either one doesn't matter. I'll just use Y. So delta P sub Y should be M Vy minus negative M Vy, which equals 2M Vy. So basically, I'm saying the initial direction is in the positive direction, or excuse me, is in the negative direction. That's why I used it this way, even though the coordinates sort of, I should have drawn it going against this wall. But the main thing is I just wanted to choose a direction that gave me ultimately a positive. So if I flip the diagram and that, analyze it hitting this wall over here, then I would get exactly this quantity, and that works fine. Now, the amount of time over which this occurs, delta T, is actually going to be basically the number of particles within a length of, let's say, 2L is going to actually be able to hit this in a given time interval. So the delta T is really the distance divided by the velocity. So that's 2L over the velocity, which I say is Vy. Okay. Now, F, we know from Newton's second law, is delta P over delta T. So we're going to say this is delta MV over delta T. In this case, again, we're just taking the Y direction. So I'm going to say the delta MV, of course, is 2MVY. And then the delta T is going to be 2L over Vy again. So ultimately, I think you can see what you're going to get. You're going to get the 2's actually canceling out, and you'll get MVy squared over L. So that's the actual force. That's the force to a single molecule, and basically any molecule within 2L. In other words, any molecule all the way from here all the way back to there. Any one of those molecules, long as Vy is big enough to be L over, Vy is big enough to be L over 2 delta T, then you can know that it will hit in the time interval. With that, we can now start to think about pressure. And of course, we can also make it a little less about Y. We can take into account the fact that this is going to be true for, in fact, each of the directions. So this is for the Y direction that we just got. So we might actually realize, hey, wait a second, F is going to be M over L times Vx squared plus Vy squared plus Vz squared. Does that make sense to everyone? And in fact, it's going to be that just for one molecule, but F total for all the molecules would be M over L times V1x squared plus V1y squared plus V2 or V1z squared plus V2 x squared plus ... In other words, I'm going to do 3 terms for every molecule in existence. So I'm actually going to get a mess load of actual forces here, or actual terms in the forces, but that'll give me the total force. And if I look at it, I can realize, wait a second, Vx squared, if I wanted to take the actual average of the square of the velocity, then I could take and say Vx squared plus Vy squared plus V squared. Notice that's just the average velocity squared. Notice with no subscripts, in other words. So if I wanted just the velocity averaged, then I could say, okay, well, this is just going to be Vx squared 1 plus V2x squared plus V3x squared plus ... on up to Vnx squared. And then if I take all that and divide it by the actual n, then that will give me the average of the square of the velocity. But we also know, because Vx plus Vy plus Vz, when I square all those and add them up, I know that Vx squared plus Vy squared plus Vz squared, let's say for particle I is just Vi squared, right? The sum of the squares of the individual three-dimensional components is actually equal to the actual velocity. So I can now say that V squared is actually equal to Vx squared plus Vy squared plus Vz squared. Again, taking the individual averages of each of those squares. And if I make the extra special understanding that statistically speaking, we're talking not a billion, not a trillion particles. We're talking particles in number of around 10 to the 23rd, okay? 1 followed by 23 zeros. That's the perfect statistical ensemble. Therefore, it's extremely unlikely that Vx squared would be different on average than Vy squared or Vz squared. So the equal partition theorem suggests that Vx squared is equal to Vy squared is equal to Vz squared, right? What's the odds of having 1 with 22 zeros after it items and the average of all the X components is significantly different from the average of all the Y components? It's nil, right? So by making that assumption, then we can come up with some pretty cool conclusions. And the conclusions are ultimately that this force that I had, that F that I was talking about earlier, that total one, which I'm just going to call F in a second, so I'll just call it F, that's going to be basically the M over the L that I had before, the M over the L, notice the M over the L. And now in this case, I'm going to have to multiply it by N because there's N particles, and then I'm going to multiply it by Vx squared. And since Vx squared is equal to Vy squared is equal to Vz squared, I can change that a little bit as well and say it's actually going to be equal to 3 M over L times N times V squared. And the reason I do the 3 is because this quantity is for Vx, then there's another quantity just like it for Vy, and then there's another quantity just like it for Vz. And since they're all equal, that should be 1 plus another, which is 3 times as many. So I'm ultimately going to say V squared average. Now, if I want the actual pressure is equal to force divided by area. And since I used a cube, the area is in fact L squared. So F should be, P should be F over L squared. So with this, I get 3 M N V squared average over L cubed. Okay. Actually, I got my 3 in the wrong spot. What happened? That should be right. That should be right. I did right here. Let's see. Vx squared plus Vy squared plus, yeah, that works. And this works here. Oh, duh. Okay, gotcha. Yeah, my fault. This should not be 3 times as much. Remember, I've got Vx squared plus Vy squared plus Vz squared. All of those add up to give me V. So I actually got to divide by 3, not multiply by 3. Sorry about that. I was remembering an entirely different derivation. So everybody understands why I got 3, because it takes 3 of these, an X, a Y, and a Z, to make one V. And I'm trying to convert this ultimately to just V, not Vx or Vy or Vz. So that's why it's 1/3. Sorry about that. Now that I've got that, I can now say, all right, well, this looks like something that's fairly useful. I can say N, the number of molecules or atoms. I can say times 1/3, which we don't really know what that means yet, but I'll explain it in a second, times mv squared over, and now we have, of course, F divided by L squared would actually be L cubed down here in the bottom. So with this in mind, we can all of a sudden say, oh, wait a second, L cubed is the volume. So I can say pressure times volume is equal to 1/3 of 2 times 1/2 mv squared. Again, the bar should be there for averaging. And then times N. Okay, notice what I did there. I wanted a kinetic energy term, and kinetic energy is 1/2 mv squared. So I multiplied by 1/2 while simultaneously multiplying by 2. Okay, so multiplying by 1/2 and multiplying by 2 at the same time gives me something that's reasonable. I can now say that PV, as your book uses it, the capital P and the capital V, in that case is going to be 2/3 times, now we're going to multiply that by the number of molecules or atoms here, and then times the average kinetic energy, 1/2 mv bar squared. So this is really kinetic energy average. Okay. But according to the version of the ideal gas law that I just gave you, PV is equal to N times KB times T. So I can see, well, there's my N, there's my P and V. So the 2/3 KE times the average kinetic energy must be equal to KB times T. I think that's right. I feel like I should have a 1/2 or something. So 2/3 times the average kinetic energy. Oh, yeah, there's an extra factor of 2 in there that should be. No, that's okay into it. Those 2/3 in it. Yeah. Okay. So now that I have that, I actually have an expression that the average kinetic energy, 1/2 mv squared, oh, is 3/2. So the average kinetic energy is actually equal to 3/2 kT. Now, what that 3/2 means is 1/2 of a kT goes to each degree of freedom. So I can go left, right, that's a degree of freedom. I can go in, out, that's a degree of freedom. And up, down, that's a degree of freedom. Those are all the translational motions. So this is all the kinetic energy of molecules moving in straight lines. Now, molecules can also have their atoms bouncing together. That's another degree of freedom, but that doesn't count in the temperature. Only these 3 count in the temperature. They can also spin about an axis. That, again, is another degree of freedom, but that doesn't count in the temperature, okay? That's why water, which is a molecule, it's got sort of a big high oxygen and then 2 hydrogens. It can actually oscillate about these two. It can oscillate about these two. It can spin about this axis. All those extra degrees of freedom are ways that it can absorb heat without raising its temperature. That's why the specific heat of water is so high. All right, so that's it. I know we've ran a little bit past, well, actually 6 minutes past the end of our class, so I apologize for that again. But we've now gotten into at least the part where we can start solving problems for chapter 18. We basically got through page 478. There is a problem that I listed. I will keep it on there, but we'll solve it next time. The number 8 or number 1 part for 18. That'll still be in the Word document that I post on in my Google Docs. But anyways, you folks are actually free to go, but I'll wait for the last one to leave in case y'all have any questions. And I apologize for running over. I should have paid more attention to the clock. Jamie, you have any questions, bud?
No.
All right. Well, that sounds wonderful. Hopefully I'm doing a good job. I'm explaining it and y'all can understand it, but I know it's going fast, so I get it if it's hard.
Thank you, Professor. Have a good night.
You too, Sean. Have a good one.